Okay, section 5.3 is continuing in your notes on page 58. And we are talking about higher derivatives, which will give us the concavity, and then we'll discuss the second derivative test. So it's a very smooth continuation of section 5.2, continuing on from relative maxima and extrema. So just a little review here. Let's list the four derivatives, the first four derivatives of f of x equals x to the fourth minus 5x cubed plus 7. So finding higher derivatives, we are just taking the derivative, the same rules that apply before, to each consecutive derivative. So if we find our first derivative, we would get 4x cubed minus 15x squared, right? So we continue taking derivatives. So now we're taking the derivative of the first derivative, and we would get 12x squared minus 15, not 15, minus 30x. Then the third derivative, we are taking the derivative of that, and we'd get 24x minus 30. And beyond that, we generally just write the number of the derivative in parentheses, where the derivative symbol is here. So right here, that's a 4 in parentheses, and we would get simply 24. Okay, now for our derivatives, if velocity is the rate of change of position, so remember our first derivative is like slope, okay? So if our original function value is the position of a term, of a object, then the first derivative would be the velocity, right? The change in speed, or the change in speed, right? So the second derivative would be the rate of change of velocity, which is called acceleration. So how much are we increasing or decreasing in speed? Okay, so the change in the change of speed, again, that's called acceleration. So if our position function is f of t, the velocity, we're looking right here, would be the first derivative in terms of time, and our acceleration would be the derivative of the velocity, which is the second derivative of our position function. So look at these graphs. So this is the original function, the derivative function, and the second derivative. Okay, notice that in our first function we have this nice curve, right? Where our position is increasing, we have a relative max and we have a relative minimum. Now, when we're looking at just the change of slope, notice we have a positive slope until we hit value A. So we are above the y-axis until we hit this value A, okay? Then we have a negative slope through to B. Let me switch my colors. So we are decreasing until we hit value B. Let me fix that a little bit. So that would be here below the y-axis. And then we have a positive slope. Again, where we're increasing. So our first derivative, we can see that is true. Okay. Now, if we're looking at our first derivative now, okay, so the middle value where we have a relative minimum, we can see our slope of this function is negative until C, right? So our velocity is decreasing, okay? Our change in velocity is decreasing, I should say. So it's negative below the y-axis, and then our change in velocity is increasing, okay? Our slope is positive, so we are above the y-axis in the next portion. I guess I probably should use a different color. Here we're positive, here we're above the y-axis, okay? So all of these things are related to one another. All right, let's put this more in. These are just vocabulary terms. So this first portion where A is the relative maximum would be concave down, okay, like the top of a mountain. And concave up, like a bowl, would be here. Now, oh, you know what? It says it right here. Okay? Silly me. All right. So if we look back at our graph, yes, our tangent line here would be above where our graph is, and here would be below. That's all that's saying. So again, looking at the graph right here. Okay, so our concavity is changing there, right? Which you can see where that looks like on the second graph. We're changing our slope of the derivative is changing, and notice here it's 0. Sure? No words. It says, okay, so when we're talking about what this looks, it looks like we're concave up at the bottom of the valley, where concave down, we didn't discuss this. We'll go back to the previous slide and discuss this. Looks like the top of a mountain. So also, concave up has its tangent lines below the graph, while concave up has them above the graph. Okay. It says x equals c, okay, seems to be a point on the graph where it changes from concave up to concave down, and that the second derivative of c is 0. So that means c is called an inflection point. Now, there's two things that must be true to have an inflection point. The first is that the second derivative at this critical, or this point c, must be equal to 0. Notice it says that right there. Or like our previous critical points, or is undefined. Okay, notice that c must be in the domain, just like before when we're looking at our first derivative for the change of slope. Okay, and also then c would be where the concavity changes. If you can read my writing, c is where the concavity changes, as we saw in the graph. True. Okay. So here's an example. Find any inflection points and describe the concavity for f of x equals 2x cubed minus 6x squared plus 7x. So our first derivative, so to find the inflection points, we want to find the second derivative, set it equal to 0, and then check either side of 0 to see where the concavity is. So the first derivative, we would get 6x squared minus 12x plus 7. Our second derivative, we would get 12x minus 12. So we want to set the second derivative equal to 0. So 12x minus 12 is 0. We can see x is 1. So if we look at our number line, again, we're checking the value in the second derivative. So we could check something smaller than 1, which would be 0, for example, in the second derivative. So we're plugging it in here, and we would get a negative. Now remember, negative means concave down, which looks like this. And if we check something greater, like 2, we would get a positive value. So we would have concave up, like so. Okay. Now, so that would mean that, what is it asking us? Finding inflection points and describe the concavity. So our inflection point is x equals 1, and we are concave down from negative infinity to 1. Again, we use a parenthesis. We don't really define whether we're concave up or down at 1 because it's a changing spot. And then we are concave up from 1 to infinity. Okay. Now, often it will ask us when we ask us for the inflection points, I should go back a little bit. It usually wants the y value as well. So we would plug in 1 into the function, and we would get 3. So our inflection point should actually read the 0.13. Okay, plug in 1 here. We get 2 minus 6 plus 7. Negative 4 plus 7 is 3. So that would be our inflection point. All right, another example. Same instructions. So we want to find the first and the second derivative. So our first derivative would be 15x to the fourth minus 20x cubed. Second derivative would be 60x cubed minus 60x squared. So now we want to set this equal to 0. So we can factor out a 60x squared from each of these terms. We would get x minus 1. So we have two potential values, x equals 0 and x equals 1. Okay, let's look at a number line. Again, these are potential, not necessarily are a change. Okay, so if we plug in a value less than 0, say we want to check the second derivative of negative 1, we would get a big negative number. Okay, so that means here it's concave down. If we check something in between 0 and 1, say a half, we still get a negative value. Okay, so it's still concave down. If we check something greater than 1, say 2, we get a positive number, so it is concave up. Again, you can check all my work if you want to actually plug in those values. Use your calculator. Remember, we're plugging it in to our second derivative now. So we're plugging the values in here. Okay, so now notice this 0 is not an inflection point, right? Because the concavity did not change on either side of it. Okay, so we have one inflection point at the value x equals 1. So to find our inflection point, we also need a y-coordinate. So we could plug g of 1, again, the original function, we would get 3 minus 5, which is a negative 2. So our inflection point is 1, negative 2. We are concave down from negative infinity to 1. And we are concave up then from 1 to positive infinity. Okay. Now it says the second derivative test can be used to find a relative maximum or minimum as well. Okay. Notice our concavity, if it's concave up, we have a shape that looks like the bottom of a hill, right? So that would be pointing towards a minimum value. And if we have it concave down, it looks like it's a maximum. So if f of x has a horizontal tangent at a location which is concave up, then f of a would be a relative maximum, and reverse if it's concave. So concave down, would be relative max. If it's concave up, the function value at a would be a relative minimum. Therefore, the first derivative is used to find the critical numbers. And then we can check those critical numbers in the second derivative to show whether it's concave up or concave down. So again, we still use our first derivative to find these critical points, but then instead of checking them on a number line and checking whether the slope is positive or negative there, we can instead use the second derivative to determine what the shape of the graph looks like. And that would tell us whether it's a max or min. Okay, so either method is fine, but both would work. All right, so let's try it this way. So the derivative of f of this function, f of x equals 3x cubed minus 9x squared. Our derivative would be 9x squared minus 18x. Okay, so to find our critical numbers, we want to set this equal to 0. We can factor out a 9x from each of these. We get x minus 2. So we have x equals 0 or x equals 2. Okay, So now we can check the concavity. So in order to do that, we need the second derivative. So the second derivative of x is 18x minus 18. Okay, so if we check our first value of 0, we get 0. Nope, we don't. Silly me. If we check 0, we get negative 18, which means it's concave down, which looks like this. So what would that mean? That means this value here, 0, is a relative maximum. Okay, so we have a relative maximum at x equals 0. If we check the second derivative at our critical point 2, we have 18 times 2 minus 18 is positive 18, which means it's concave up, like so. Okay, so that would mean we have a relative minimum at x equals 2. So another way of finding our relative max and min. Okay, our next example, we are on page 60 of our course notes. It says find the second derivative at 0, and the second derivative at 2. Okay, so we're not asked to find too many things, just to plug in these values. Okay, so when we find the derivative of this, we have a quotient, so we would take the bottom term times derivative of the numerator minus the numerator times derivative of the denominator, which is just 1, divided by the denominator squared. So if we simplify that, we have 2x plus 2x squared minus x squared over 1 plus x squared. Again, simplify that. We get x squared plus 2x. Okay. Now notice that if we simplify this, we could factor out an x. We'd be left with x plus 2. Oh, that doesn't help us. Never mind. I was thinking to be left with x plus 1, which would cancel, and it does not. Okay, so that's our first derivative here. Okay, so we want to now find the derivative of that term. Okay, so same thing. We take derivative, or the bottom times derivative of the numerator minus the numerator times derivative of the denominator. So we would have 2 times 1 plus x, decrease the exponent, and then multiply by what the derivative of the inner function, which would just be 1. So I'm going to skip it. Divided by 1 plus x squared, quantity squared, which would give us a 1 plus x to the 4th. Okay, we have some simplifying to do here. Now, there are different ways you could do this, but notice that we have a 1 plus x, 1 plus x, and a 1 plus x. So the first thing we could do is to cancel divide each term by that, or in other words, what we're doing is we're factoring out a 1 plus x from the numerator. So we'd be left with 1 plus x times 2x plus 2. Minus 2 and x squared plus 2x. That 1 plus x here is gone. And then we'd be canceling that with one of our denominators of the 4. Okay, so now I'm going to continue on a new slide. So we are going to be canceling this and one of these to become a 3. Okay, so we have the second derivative is equal to now 1 plus x times 2x plus 2 minus 2 times x squared plus 2x, all divided by 1 plus x to the 3rd. So we can multiply out this, FOIL out this first term, these first two terms. So we get 2x plus 2 plus 2x squared plus 2x, and distribute the negative 2, and then see what cancels. So you can see that we have a 2x squared and a negative 2x squared. We have positive 2x, and negative 4x. So 4x minus 4x is 0. So those are gone. So our final simplified version of our second derivative would be 2 divided by 1 plus x quantity cubed. So now it asks us to evaluate the second derivative at 0 and at 2. So the second derivative at 0, if we plug a 0 in, we simply get 2 divided by 1 plus 0 cubed. 1 plus 0 is 1. So 2 divided by 1 cubed is simply 2. And our second derivative at 2 would be 2 divided by 3 cubed, or 2 over 27. All right, part B. Same instructions. Our original function is 32x to the 3/4. So our derivative, we would multiply 3/4 out front and subtract 1 from the exponent, getting negative 1/4. So if we simplify that, 3/4 times 32 is 24. So we have 24x to the negative 1/4. And then we want the second derivative as well. So we multiply 1/4 out front and minus 1 from the exponent. We would get negative 5/4. So negative 1/4 times 24 is a negative 6. And then we want to evaluate this at 0 and at 2. So remember though, let's rewrite this. Our second derivative is equal to negative 6 over x to the 5/4, which would be negative 6 over the 4th root of x to the 5th. Now notice we cannot plug a 0 in the denominator, right? So the second derivative at 0 does not exist. D and E does not exist. So let's find it at 2. If we plug a 2 in, we would have negative 6 over the 4th root of 2 to the 5th. So that would be the 4th root of 32. And 32 is equal to 16 times 2. The 4th root of 16 is simply 2. Keep simplifying. We would get negative 6 over 2 times 4th root of 2, which could be simplified to negative 3 over the 4th root of 2. Lots of algebra review. All right, this next example is really just asking us for the third and fourth derivative. So let's do that. Find our first derivative. We would be 28x cubed plus 18x squared plus 10x plus 4. Second derivative, 28 times 3 is 84 plus 36x plus 10. Third derivative, which is one of the things they're asking for, would be 168x plus 36. And lastly, the fourth derivative would be simply 168. Okay. For the next 3 problems, it says to give the open intervals where the graph is concave up, concave down, and list any inflection points. So we don't actually have the algebra to do here. We are just looking at a graph and interpreting. So notice at this point, 2, 3, we're changing from concave down to concave up. So we are concave up on this portion, and we are concave down here. And then our inflection point is at 2, 3. Okay, so we're concave up from 2 to infinity, concave down from negative infinity to 2. And that's all it's asking us for. The next graph is not quite as obvious because the shape is a little bit different, but we do consider this portion here concave up. So it's continuing on forever, right? And it's more of a concave up than a concave down. And then our concave down here would be this portion of the graph. Notice there is no inflection point because we're changing at this vertical line x equals 2, but there's no actual point. So we can have a change in concavity without an inflection point, right? Because the function value does not exist at x equals 2. But we are still concave up from 2 to infinity and concave down from negative infinity to 2. Okay, part C. This one does not have a graph for us. It just has a function. Notice it's the same one. No, it's not. It looks very similar to the equation we found the third and fourth derivative for. Okay, so the first derivative, we would get negative 6x squared plus 18x plus 168. And then we want our second derivative to find our inflection point possibilities. And we get negative 12x plus 18. So to find inflection points, we want to set this equal to 0. Subtract 18 from both sides, and we would get x is positive 3/2. So we're going to check our second derivative values to the left and to the right of this. So something smaller than 3/2, again, I always pick 0 if possible. The function value, again, we're looking at the second derivative, plugging it in here. At 0, we would get positive 18, which is positive. That means concave up, like this. And if we check something larger, say 2, we would get a negative value. So that means we are concave down, like so. Okay? So when we write our answer, our inflection point is x equals 3/2, but we want the whole point, so we plug in 3/2 into the original function. Okay, again, the original function. So we have negative 2 times 3/2 cubed plus 9 times 3/2 squared plus 168 times 3/2 minus 3, running out of room here. And if you do that, we have 525 halves, or you can use a calculator and get a decimal value as well. It would be 262.5. So our inflection point is 3/2, 525 over 2. And then we are concave up from negative infinity to 3/2 and concave down from 3/2 to infinity. Okay, I'm missing this one. Okay, so part D, yeah, we're on page 62 of your course notes, says f of x equals 17x minus 17e to the negative x. Okay, so if we find our first derivative, we would have 17. Now, we have to remember our derivative rules here, but we will get a positive 17e to the negative x. So if you remember, we take the derivative of e to the negative x is e to the negative x natural log of e times the chain rule derivative of the exponent is a negative, which is why our sign flipped. Very similar to the second derivative. Derivative of 17 is 0, but our sign will flip again when we take the derivative of e to the negative x. Okay, so when is this equal to 0? Well, no matter what we plug in for x, it will never be equal to 0. So there's no solution to this. Okay, so that means we could just check the second derivative for anything. Like I pick 0, something easy. If x is 0, e to the 0 power is 1. So we would get negative 17, which is negative, which means the whole graph is concave down. So no inflection point. Okay, and the graph is concave down from negative infinity to infinity. A couple more examples. Okay, last example for this section. For f of x equals 2x cubed minus 4x squared plus 2, find any critical numbers and use the second derivative test to determine any relative maximum or relative minima. So we're not looking for inflection points, we're looking for our relative max and min. Okay, so finding the second derivative, or finding the first derivative and finding critical points. So critical points is first derivative. Okay, concave up and concave down. Inflection points is second derivative. Okay, so we have 6x squared minus 8x. We want to set this equal to 0. To solve this, we could factor out a 2x, left with 3x minus 4. So we get x equals 0, or x is 4/3. Okay, so now we find our second derivative to determine the concavity. And whether it's concave up or concave down will tell us whether these critical points are relative maximum or relative minimum. So our second derivative is 12x minus 8. So if we plug in 0, our first critical number, we get -8, which means it's concave down, right? Shaped like this. So that means our critical point where the slope is changing is a relative max. Okay, and then we can check the second derivative at 4/3, and we would get 12 times 4/3 minus 8 is equal to 8. So that means it's concave up, which means x equals 4/3 is a relative. So concave up looks like this. So that means where we're changing slope is a relative minimum.